Hello, my name is Eden Kim. I'm CEO of Calypso Systems, Inc., and I'm here to present optimizing SSD performance with artificial intelligence and real-world workloads. I want to welcome you to this virtual FMS. So today we're going to look at an example of how to capture a GPS navigation edge workload and use it to optimize artificial intelligence, machine learning, LSTM, RNNs. LSTM stands for long short-term memory, and RNN stands for recurrent neural networks. We will be capturing and looking at workloads on the input side of LSTM RNNs, as well as on the output side to see the characterization of the workloads. However, this talk will not delve into the mechanics inside the artificial intelligence analysis and optimization, as that's outside the scope of this work. So what's the difference between a synthetic and a real-world workload? Well, synthetic workloads are typically corner case workloads that stress storage outside the range of normal usage, whereas real-world edge workloads are a constantly changing combination of different IO streams and queue depths. Synthetic workloads tend to be a fixed or single very few IO stream workload applied over a defined period of time. Real-world edge workloads may have many IO streams, hundreds to thousands, that change over the course of the workload. Corner case workloads have traditional transfer sizes, such as half K, 4K, 8, 16, 32, and so forth, up to 1 megabyte, whereas real-world workloads have many non-typical transfer sizes, such as 10 byte, 28 byte, 60 byte, 128 byte, 1K, 1.5K, 20, 36, 56, and so on and so forth. Corner case workloads also have a fixed demand intensity or queue depth. On the other hand, the real-world workload edge workloads have a constantly changing demand intensity or queue depth that varies as time goes on. So what are some examples of real-world edge workloads? Well, you have artificial intelligence, you have genetics, genomics, 3D animations, cloud storage, big data, web portals, machine learning, and 5G edge servers. Today's example will be a blend of AI, cloud storage, big data, web portal, and machine learning. So let's take a closer look at a GPS navigation edge portal 24-hour workload. So what you're looking at here is a representation of a 24-hour IO capture, or what we call an IO stream map. The first thing you'll see on the x-axis is time. On the y-axis, you have IOs, IOPS, and IO stream metrics. If you look at the colored bars going across the x-axis, you can see that there are different IO stream sizes, queue depths, and read-write mixes. Also note that there are 4 12,000 IO spikes, each of which is comprised primarily of sequential half-K writes. The blue dots are the IOs or the IOPS, and note how they're homogenously clustered around the 10,000 IO level. Finally, you can see the orange line, which is queue depths, which ranges from 7 to 368, depending on the activity that occurs on the IO stream map. If we look a little closer at the IO streams, they are listed across the top as data series, but also in the cumulative workload. Here we can see that the 9 most common IO streams by percentage of IO occurrence are listed and selected to display on the IO stream map. The other thing to notice is that there are a total of over 1,000 different IO streams that occur over the 24 hours. These are of all different sizes, 28K, half K, 1.5K, 64K, and so on and so forth. But the 9 selected IO streams that you see compose 68 to 70% of the total IOs that occur. Finally, if you look at the 9 IO streams, they have a read-write mix ratio of 94% writes to 6% reads. So this is a heavily dominant write workload. If you look at the activities that occur, we can chart the process IDs, or PIDs. PIDs are assigned by the OS kernel to each IO stream and can reflect the process, the event, or the driver associated with the IO stream. In this case, SQL Server and MySQL comprise over 80% of the IOs. So that means that 80% of the IOs are SQL Server associated. In addition to that, while not listed as a SQL Server related process ID, many of these SQL Server PIDs can be subsumed in the system IOs. So if you see there below the bubble, the system IOs are another 15%. So in addition to the 80%, some number of those system process IDs would also be SQL Server IDs. So where you capture a workload in the stack is very important. This is because IO streams change as they traverse the software stack from user space to storage and back. For this presentation, we are using the IOProfiler IO capture tools to capture the workloads. So in the first case, you can capture the IO stream workloads in the enterprise storage of the file system and see all of the IOs that are applied to the logical storage, whether it's NAS, SAN, DAS, persistent memory, computational object, or any other kind of storage. In addition to the file system, you can also capture IOs that go at the block IO level to NVDIMM, to data center persistent memory modules, to NVMe SSDs, logical units, storage clusters, hard drives, and the like. In addition to direct enterprise storage, we can also capture at the fabric. So depending on the fabric that you use, you can install the IOProfiler capture tool on the host initiator and capture all of the IOs that are going from the host initiator to the target server storage. In addition, you can put the capture tool on the target storage server, and then again, just as with the enterprise server, capture logical storage at the target storage server file system or tunnel through to the block IO layer for the individual storage. You can also look at virtual storage. Here we go at the VM level and put the IO capture tool on the virtual storage server, and then you can proceed to capture your fabric or direct enterprise storage and follow the paths as previously indicated. So again, you can capture any direct, remote, or fabric storage. You can capture at the physical, virtual, or logical storage layer. You can capture at the file system, block IO, or byte addressable. And you can capture on persistent memory, NVMe SSD, logical units, storage clusters, and more. So if you're interested in seeing the SNIA Compute Memory Storage Initiative reference workloads, or look at these IO capture tools in the analytics, you can look at them and download them for free at www.testmyworkload.com. So let's look at an IO workload capture, curation, and optimization with using the IOProfiler. Again, IOProfiler captures real-world workloads. So in the first case, we can capture time steps of IO activity and capture very fine-grained or very broad-stroke IO capture workloads. IO profiles are different than IO trace captures in that we don't take any personal data or record actual information. Because we use steps, and because we average the statistics of the IO streams over each step, we can transfer this table of IO statistics to a database and rebuild the workload without dragging over the associated large data file sets associated with IO trace captures. Using an IO capture tool, we can also monitor workloads from the edge. This edge transmission allows us to portably send small file size captures from the edge to the data center server. We can use edge transmission for real-time telemetry, and we can also use the automated phone home alert system, which we'll talk about in just a minute. With this edge transmission monitoring, we can continuously view the workloads. We can replay workloads as they happen from the edge, and we can also monitor multiple nodes, servers, and drives. Once we capture the IO stream activity, we can then look at the key performance indicators, such as the IO stream metrics, such as process IDs, IO bursts, and we can look at spikes from trim activity, from queue deaths, from boot storms, and other activity. Once we have these key performance indicators, we can then curate the workload. We can parse, filter, rebuild, or splice any workload to focus on the activities of interest to reflect the target workload as we wish to see it. Once we have a curated workload, then we can use it to train or use it for replay testing for artificial intelligence or for validation of other storage systems. So in the AI case, we use the replay of these workloads to loop, validate, and infer to optimize the performance activity. In addition to AI, we can use the captured workload and the replay test to optimize storage. This could be used for storage qualification, validation, and evaluation. Okay, so let's take a little closer look at artificial intelligence and the IOProfiler. So there are basically three parts to AI in this context. First step is gather. Here you want to gather the workload IO capture and curate the workload into a test script. The second step is training. Here you take the replay test script and you apply it to your storage and you repeat it, and then you use your AI algorithms of interest to optimize the storage. And then in the third case, you do inference. Once you have the optimization algorithms, you can then use it to infer the workload performance from the edge and optimize it for your storage. So let's take a little closer look at gather, training, and inference. For gather, again, we're looking at a long short-term memory recurrent neural network workload. We are going to gather the workload on the input layer of the LSTM RNN. So you can see here that there are many servers with real-world storage workloads that are inputting to server nodes. We capture this input activity and create training test loops, which we then use in AI optimization to help the LSTM layer optimize the performance of storage to the workload. Hidden to us are the LSTM layer, the hidden dense layer, the sigmoid activation function, and more. But what we see is on the output layer, workloads coming out to other nodes. So we can capture the input and the output to this LSTM RNN and use those workload captures to either train using the replay test or for validation or inference, looking at the output layer to make sure that the output of our AI matches our assumptions and our objectives. So again, at the gather stage, we are going to capture, curate, and create a replay test script. At the training, we're going to take that replay test and we're going to apply it to the storage repetitively and keep tracking the key performance indicators to see how performance improves with each iterative step of the AI algorithmic development. So this AI machine learning workload training is a replay, test, and loop. So you can see here that you can take the input test and you can run a series of tests against the storage over time, and then you can analyze that output and then improve your AI algorithm to target the key performance indicator of interest. We're not going to peel back the layers and look under the hood to see which key performance indicators were used in this case, but it was looking primarily at the data transfer size or the block size and the queue depth as the key determinants in optimizing this workload. For the inference or the optimization, what we see now is taking the IOCapture tool and monitoring the edge workload to see if the output layer has been giving us higher performance. So here you apply the LSTM RNN AI algorithms and you optimize your performance gains, and then you want to monitor the edge performance to see that the continuous delivery integration is achieving the goals and objectives of your AI. So here you can then see that from the edge, my workload has been improving with the orange line going up and the blue line going down. So IOPS going up, response times going down. And then you can see by grabbing individual test workloads, we can see a progression where, in this case, our IOPS are increasing from 112,000 to 115,000 over the course of 10 runs. The last aspect of this real-time monitoring of the edge workloads is to use key performance indicator or KPI alerts from multiple edge servers and nodes. So we'll have on the edge many different servers that we may want to monitor the workloads from. Because we're using IOStream time steps, we can deliver, monitor, and observe the workloads very efficiently in real time without having bottlenecks of having to move huge amounts of workload data from the edge to the data center. Further, if we set the key performance indicator monitoring up, we can have phone home alerts that can give you an alert when a threshold is met for example, a low IOPS level or a high response time level. It can tell you which node has done that. You can click that node and look at the real-time performance and then capture the workload for future performance optimization or for validation of your AI, ML, LSTM, RNN. That was a lot of letters, I know. So, in conclusion, applications and storage performance depends on the workload, and these workloads change as they traverse the IO and software stack. Real-world edge workloads are very different than your synthetic lab workloads. And you can capture your real-world workloads with the free IOCapture tools available at testmyworkload.com. Once you have your workload, you can curate and train AI workloads using the IOProfiler toolset. And you can use these replay results to optimize your applications and storage by monitoring and curating key performance indicators. So that was just a quick overview of how to use IOProfiler, real-world workload, IOCapture tools, analysis and monitoring, and in this case to AI, LSTM, RNN. So if you have any questions, you can send them to info@calypsotesters.com. Otherwise, I look forward to seeing you and hearing from you at the next FMS, perhaps not virtual, show. Thank you very much.